Okay guys, here we are looking at crude oil refining. I know we had said in the first video that we were going to eliminate as much of the oil and gas stuff as possible, but it is the basis for our organic chemistry curriculum here in Alberta, simply due to the fact that most of the hydrocarbons that we have in our fossil fuel reserves ultimately end up getting burned and turned into fuels. Very few are designated for other things. So, wanted to talk to you guys about one thing in how we separate out a mixture based upon molecular weights. This is something called fractionation or fractional distillation. Okay, term you may have heard of before. And what this is going to do is it's going to separate out a bunch of different things in a mixture based upon their unique boiling and condensation points. So if you've ever been up to Edmonton, if you've ever driven past Bowden on Highway 2, you may have noticed, I think it's a fast gas refinery that's on the highway, like just off the highway near Bowden when you're on Highway 2. And you might notice those really, really tall towers when you're there. If you've ever been near Sherwood Park in Edmonton, then you've seen Refinery Row up there, and you've seen an awful lot of these really, really tall towers. These are all what are known as fractionation towers. At least most of them that you're seeing there are. Now, what we have in a fractionation tower is usually a crude oil input. Crude oil is considered crude because it's an unusable crude mixture of just all sorts of different hydrocarbons. It doesn't burn well, it's not a good lubricant, it does nothing well. It's got all these desirable fractions or parts that we want to try and get at. There's certain ones that, make good fuels. There's ones that are better as, let's say, heavy oils like kerosene or diesel. There's ones where we're looking at lubricating oils, and so on and so forth. There's the waxes that we might also want. And all these things are mixed together. So what we're going to do is we're going to pump crude oil in, and we're going to heat it, in the absence of oxygen, to a very high temperature. All right, ones here in Alberta often use a temperature around 500 C. The video that I'm going to direct you guys to on D2L is for North Sea oils. They're talking about 375 to 400 C, whatever. So what we're going to do is we're just going to heat it up, and most of the compounds will get to their gaseous state at this high temperature, which means the moment it goes in here, most of these things are vapors that are rising. A little bit has a boiling point above 500 degrees C, and it of course will drop down and be pumped out. And you can see that these are really heavy things that might be components of asphalt, heavy waxes, and things like that. So what happens to the rest? What happens to the stuff that's rising up through this tall tower? Well, this tall tower is a coolant tower. Okay, we know that the further we get away from a heat source, the colder things are going to get. While hot air does rise, what's going to happen is it's losing energy as it does this, and so our vapors, as they rise, will start to hit different temperatures along the way, and large ones will start to condense very early. So there's your large size ones. So while they might move through this trap, they'll just rain back down into it, and then they can be pumped out. And we can see that we're into some fairly big oils here. All right, something that doesn't sound as thin and light as gasoline, something that's not, solid at 500 degrees like a wax, but we have these heavy viscous oils that we're starting to collect here. As lighter and smaller compounds continue to rise, they will condense at higher altitudes in the tower and begin to rain back down. And so these ones are smaller still with lower boiling points, and we will see them being able to be pumped off, and now we're dealing with other fuels. Other ones will continue higher, and we're getting lighter gasolines and things like that. Some keep going, condense back down, so now we're into the very small molecules, pump those off, and some are so small that they never condense, and we pump these out as gases from the top. So fractional distillation is really just taking advantage of London forces, as you might remember. And the larger the molecule, the more coalescing London forces you have, and therefore the higher the boiling point will be in degrees. So the largest molecules do not boil, do not go into a gaseous state, and they just kind of pour off the bottom. Large ones that do boil will condense early and be pumped out near the bottom of the tower. The smaller the molecule is, the higher it will go before it condenses. The smallest molecules like methane and ethane and propane might stay gaseous throughout at the temperatures at the top of the tower, and we just pump those out as liquefied petroleum gases. Okay, how do we collect them? Just this is a kind of a bigger picture of what's going on. You can see what's happening here is the gases, the things that are still warm, will bubble up and then they can move through this chamber. What's not really shown well in this picture is that we have a liquid layer. Okay, we pump out the liquids here that condense, bubbles, or the gases will move through, they will bubble through this and continue onward. If they condense, they will rain back down as the condensate, and this liquid fraction of wherever we are in the tower can be pumped out. Okay, so that's fractionation. Please make sure you take a look at the fractional distillation video. It will do a much better job than me pointing at parts of a picture. It has some very nice illustrations to go along with it to help you out. So you will have to know how fractional distillation works. You will have to know what size of molecule is generally found where, and you will have to be able to relate it to boiling points and those intermolecular forces. As we move on, okay, there's that fractional distillation video that you will see. So obviously it's still embedded in the notes too. We have other chemical processes that we could talk about. We've talked about cracking and things like that. You know, we already covered this off in an earlier section of the chapter. There's other things that we can do to our fuels to make them burn better or do what we want them to do. We're going to take that out. I'd love to get into it about the oil sands with you guys, since I used to work up there before I was a teacher. Had some pretty interesting things I could have shown you about it, but sadly we won't get that opportunity. We can talk about some of those turbo diesels and why some of them work and why some of them don't, sulfur and gasoline, but we won't. And 9.6, which is really just kind of an offshoot, just taking a look at some of those reactions with respect to combustion. That's gone too. Okay, so don't forget your Chapter 9 review. Take a look at some of those questions. We are covering off everything between 9.2 and 9.4, and one small section, 9.5, which is fractional distillation. Okay, that brings us to the end of Chapter 9. Now it's just all the practice and everything that you guys can do to get ready for your Chapter 9 test, which will be on June 1st. Okay, good luck with it, guys. Hope to see you in tutorials if you're having any difficulties.